Alright, today I'm going to talk about the Barnes-Hut algorithm and how it can be used to simulate the in-body problem. So the Barnes-Hut algorithm is extremely useful in simulating what's called the in-body problem. The in-body problem is just a physics situation where you've got indifferent bodies or particles, however you want to model it, and each particle or body exerts some sort of force on all the other bodies. Now, this it can virtually never be solved on paper because if you've got in particles running around exerting forces on everything else, you're going to have a very large system of coupled nonlinear differential equations, and there's no way you're going to be able to solve that by analytical means. So the best you can hope to do is simulate it. And simulations can get out of hand pretty fast, though, because if you've got in particles, and each particle exerts a force on all the other ones, so in other words, you have in bodies, and they exert n minus 1 forces, then you've got, if you do the direct sum, so like in introductory physics, whenever you sum all the forces, set it equal to ma, blah 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 blah, then what you've got is an O of n squared algorithm. So if n gets really big, well, that direct sum, it'll get the job done, but it's going to be very slow. And in most cases, it's going to be unreasonably slow, so you need something faster. So that's what the Barnes-Hut algorithm is going to give you. And to just jump right into it, the Barnes-Hut algorithm is going to be a tree data structure. If you aren't familiar with a tree, then I suggest, or what a tree is in computer science, I'm pretty sure you know what it is in real world, but then I recommend you watch my computer science videos or find some other ones online. I'm sure there's a lot of great stuff out there, but to just dive right in, it's going to be a tree data structure, and if we build our tree in the right way, then what's going to happen is we're going to be able to compute our force in O of n log n time, which is considerably better than O of n squared. So that's what we're going to be aiming for. So to build this tree in 2D, which is what I'll be talking about in this video, you can do it in 3D as well. In 2D, it's essentially a quad tree, which means instead of every node having 2 children, like a binary tree, you're going to have 4 instead. And to build this tree, just like any other tree building algorithm, we're going to put our nodes in one at a time. Well, I should say bodies. We're going to put our bodies or particles one in at a time, and we're going to do it based on this recursive algorithm right here. So the base case for our algorithm, because if we're going to have a recursive algorithm, it better have a base case or else you're not going to end. You're just going to keep on going over and over and over and over again, and that's not going to be a very useful algorithm. It'll never terminate. So our base case is going to be, if our current node is empty, then we just put that body there. Pretty simple. Oh, I should mention, my bad. Whenever we're building a tree, we always start at the top of the tree. So whenever we first have our empty tree that just has an empty node at the top, then we're just going to put that first body there. So if we put the body A in first, then that's our first step in the algorithm. So just to draw this out as a grid, if our body A was here, this node is going, this first node right here after the first step in our algorithm is going to contain quite a bit of information. It's going to contain the mass of all the particles in the node. It's going to record the center of mass, which if we just have one body, then that's just the x and y coordinate of the mass. And it's also going to record some spatial information as well. We have to specify 2 points. We have to specify a location in space, and then a side length. We're going to be be dividing the space into squares. And so each square is going to have a side length and an absolute position in space. So we could call this point 0, 0 if we like. And if we unitize our space, then we would say like the initial side length is just 1. So yeah, each node is going to contain the physical information, the mass, center of mass, and also its position information. So its absolute location in space, and then the side length. Note that we don't have to specify all 4 corners of the square. We can just specify, for simplicity, the top left corner. Because if you know the top left corner, and you know each of these is going to be 1 away, well, you can easily pin down where all the other corners are. So it is sufficient just to name 1 point in space for our square, as long as our other nodes respect that. Which is why we're going to be using a class for this as an object-oriented programming. So now that we get the basic idea of what each node is going to represent, we can go to the second step of our algorithm. So if the current node, so remember we're starting at the top node and going down. If the current node is an internal node, so in other words, if it doesn't directly contain a body, it just contains other ones. Like for example, if we put another body in here, we want each node to only contain 1 body. So each time we have 2 nodes in 1 body, or 2 bodies in 1 node, we want to subdivide, which I'll elaborate more on in just a second. But if the current node is an internal node, so in other words, this node that we were talking about earlier, it's going to record 0, 0, the absolute location, and the distance of the square, the length of the square, I should say. It's also going to contain the 4 children right here. Because like I said before, it's going to be a quad tree. So it's going to contain the nodes of its 4 children. So if at any point in the algorithm you're at an internal node, then you need to update the center of mass and the mass of the internal node, and then just put the body in the right quadrant. But otherwise, if it wasn't empty, so in other words, like our example right here, I told you we had to divide. Here's how exactly we're going to accomplish that. So if we initially had our body A in this node right here, and we want to put the body B in this quad tree, well, I told you we couldn't put 2 bodies in the same node, so we're going to have to subdivide into 4 smaller ones. So we'll replace that A node from the beginning with not quite an empty node, but just one that has the spatial information and the center of mass and mass of the two bodies, so of A and B. So even though I'm labeling this as like it looks empty, it's secretly containing our position information like before, so that 0, 0 location. And it's also containing the length of the square and the 4 children. And the physical information, the center of mass of A and B, and the total mass of A and B. So I said we're going to split into 4 quadrants. And these are going to be initialized, these nodes right here, as empty nodes, well, nodes that don't have a body, but we'll be able to specify our location, because if we're going to split it up into 4, then each one is going to have side length s over 2, and then we'll be able to specify the absolute location, so of that top left corner of each child, by using the previous information that we had. Because we previously said the side length was s. So if we're going to subdivide, each square is going to have side length s over 2. Well, this point right here, it would just be the x-coordinate of the previous one plus x over 2, and then not adding anything to the y component. This one right here would be the converse. We'd be adding s over 2 to the y component, and this one right here would be adding s over 2 to both the components. And so after we split up into the children, then we have to put them in the right quadrant. So just to make things a little bit simpler, we'll say that the top left node is going to be the first one, top right is going to be the second one, bottom left is going to be the third one, bottom right is going to be the fourth one. So after we subdivide, then we need to put A in the first one and B in the last one. And then after we're done, we update the center of mass and mass of the internal node up here. And it's important that you do it afterwards, because if you implement it this way, you're going to get a really weird bug if you try to update it before. I'm speaking from experience here. And in the description, I'll have the link to the code. Programming this was extremely difficult. It's conceptually easy, but there'll be a few links in the description to help you out with it. So after we build our tree, how are we going to go about computing the force? Because that was the original problem. Well, to compute the force, what we're going to do is approximate it, because doing a direct sum is going to give you the most accurate results, but it's going to be very slow. So this algorithm is going to trade a little bit of accuracy for a whole lot of speed. So although it's not going to be quite as accurate as a direct sum, it's going to be more than worth it. So for each of the bodies that we intend to simulate, we're going to do this breadth first traversal of the tree that we end up with. So this tree right here, for this example. So for each of the bodies, if the current node, so we start at the top, and what we're going to say is if the current node is an internal node, so this node is an internal node because it doesn't contain a body, but it contains children. So if the current node is an internal node, and it's far enough away from, I guess we'll just start with A. So we'll say if it's far enough from A, then we're going to compute the force using the center of mass and the mass of this node. Because remember, this is storing position information of the square and also the center of mass and mass of all the bodies below it. So if that condition is met, then we're going to approximate the force by using the center of mass and the mass. But if it's not, then we need to compute the force caused by the four smaller quadrants. So we'll say that's the case just to see all the different steps here. So let's say this one is not far enough. So the center of mass, let's say it's like here, and we say, that's not far enough away. We need to get a better approximation. So what we do is we visit all the children in a breadth first manner. So we'll visit A, the one below that, and this one. And if we see this one, so H is all by its lonesome over here, if the current node is an external node, so in other words it doesn't have any children, this one doesn't, then compute the force directly. So we're left with no other option because, it doesn't have any children, so we've kind of hit the end of the line. That's why it's going to be our base case. Then we just compute the force directly. And on this node, so let's say the center of mass of E, F, and G, if that's far enough away from A, which let's just say it is, then we're going to approximate the force caused by E, F, and G by using the center of mass and the mass of E, F, and G. So if we do it this way, then we never have to compute the force caused by E, compute the force caused by F, or compute the force caused by G. So here you can kind of see that we're actually saving time here. It's at a tiny cost of accuracy, but it's more than worth it. So whenever we visit this node right here, so we have to look at all of its children. Well, first off, we have to look at the center of mass. And let's say the center of mass is right here, and that it's not close enough to A. So then we'd have to visit all of its children. And then, let's see, D. Well, D is all by its lonesome over here, in this cell right here. So we've reached the end of the line, and, well, we just have to compute the force directly, which is our base case. So we would compute the force directly and add it to our net force. And then these are empty, so they're not going to cause a force. And then we get here and we say, is the center of mass of C and B far enough away? Well, let's say that it's not. Well, then we'd have to visit the children, and then those would be at the end of the line, so we would add the force caused by B and C. So we would then repeat this algorithm for all of the nodes, for all of the bodies, I should say. And that is the algorithm, but how do we specify how something is far enough away? Because I wasn't being very precise when I was saying that. I was just saying, oh, maybe if it's close enough, or maybe if it's far enough away, then we'll use the center of mass Otherwise we won't. But how do we quantify that? We're going to quantify it by computing a certain ratio. We're going to, for each node that we come across, well, all the internal nodes, because 2 and 3 only apply to internal nodes. If we get to an external node, we just have to compute the force directly because we're at the end of the line. But if it's an internal node, then we compute this ratio, which is going to be S. So the node that you're at is going to have an associated side length, S, and we're going to divide it by the distance to the body that we're interested in. And if this ratio, this S over D ratio, is less than some predetermined value, then that's how we're going to define if it's far enough away. Which should make sense, because if the distance is really big, but the side length is small enough, so like for example D right here, the distance is going to be where that it's in. So that's how we can get a measure of how far away it is. And for most purposes, you want to choose values of theta that are not too big but not too small. Because if theta, like if you set theta exactly equal to 0, well then you're just doing a direct sum, and that's going to run an O of n squared time. So if we want that O of n log n like I promised you, then we're going to have to pick a reasonable value of theta. So most of the times you want to pick values of theta that are about like 0.5, or I've also seen like 0.7 used. The bigger the value, the more you approximate using center of mass, so the less accurate it is, but the faster it is. And conversely, if you pick a smaller theta, then it's going to be more accurate because you'll be doing more direct sums, but it'll be quite a bit slower. So that's why you want to pick good values like 0.5 or 0.7. So now we're finally at the end. So I said for complexity that the building the tree is going to take n log n time, because if you're inserting n bodies, and the worst case scenario is that you have to, because it gets divided into 4 each time, so the furthest you can go down the tree is log n. So whenever you build the tree, it's going to be n log n time. And computing the force is a little bit more tricky because it's, I guess you could say it's technically O of n squared, because if you choose your theta to be 0, then that's a direct sum. Or like if all the particles are like extremely close together, which most of the time they're not, so it's not entirely like a physical situation, then it'd be n squared. But for most purposes, it's going to be O of n log n. So I recommend you to try to code this yourself. I'm not saying it's going to be easy. I've been programming for quite a while, and I think it's one of the hardest things I've ever programmed, but it'll definitely be worth it. So let me know in the comments if you get it working. See you in the next video.